Well, the laws of attraction in physics are almost universal. Newton had it right. I mean, I'm not sure he was actually a guy who liked the Valentine's Day, but basically any large object that has mass has a gravitational attraction. It's inversely proportional to the distance and proportional directly to the mass. So if I have two large things like a sun and an earth or a moon, they're all attracted to each other, not significantly different than, say, a student in a physics class is attracted to the student next to them in the physics class. And they both have mass.
And the closer the masses are, the stronger the attraction.
The closer the masses are, the stronger the attraction.
Because we do see in romance that they say that unlike charges attract. How does that exactly work in physics?
It's the same sort of phenomena that you might see when you're actually looking at magnets. The bar magnets that we actually played with in elementary school, the North Pole and the South Pole has an electromagnetic field that moves around that bar. And that electromagnetic interaction is the thing that actually either pulls these two together when a magnet sticks with another magnet, or pushes them apart when they're actually the same pole.
The same individual magnet that is attractive to one end will be repulsive to another, almost like you are now. But, as I understand it, just like with humans, the little tiniest force can have the biggest, strongest impact. Just like the tiny things in a relationship, the tiniest forces. Is that right?
Well, in short distances, that's right. The weakest force happens to be gravitational, but the strongest force happens to be strong. So, for example, if I take a proton and I look at the things that are inside of that proton, which is what we do here at Fermilab, I will be looking at things that we call partons, or better known as quarks. If you try to dissociate these quarks from each other, that is to say, I have a quark here, and I have a quark here, and sometimes three quarks, and I try to pull them apart, that is to dissociate them, they create another particle, which is called, wait for it, gluons. The glue that sort of holds these particles together. So in some sense, that's an attractive material to some extent that holds the particles together. And as you pull them apart, you create more gluons.
So it's sort of like your daughter is dating some knucklehead, and the harder you try to talk her out of it, the more she clings to him.
It's an amazing correlation, isn't it? An amazing correlation.
I guess this physical world at various scales has many things in common.
So from one end of this spectrum, you have basically the smallest particles that are so small they don't even have geometry. And those particles are held together tighter than the largest particles that exist in our universe that have geometry. So as I pull galaxies apart, further and further apart, or pull massive planets apart, the force never goes to zero. It just goes to be very, very small.
So like with my true love Sharon, no matter how far apart we are, the force of our love remains to connect us. And the closer we get, the stronger that attraction becomes. And they say that kissing is a way of getting so close to someone you can't see their flaws.
There is a point at which you stop thinking about physics when you get that close.
Well put. And that's a great point to stop. Thanks so much, Dr. White. Appreciate it.
You're most welcome. Happy Valentine's Day.
Happy Valentine's Day.